is by Mayuri. Mayuri is talking to us remotely from Bangalore, and the talk will be about the space-based plans that we will hear from Mayuri now. Mayuri, you may please proceed with your talk.
Thanks, Prabhu. Yeah, just tell me when I can start and I'll go ahead. Okay, great. All right. Thank you, Prabhu. Thank you, organizers, for inviting me to present this talk, and also for making an accommodation for me to present this talk remotely. So thanks also to the audience for their patience. So I've been asked to talk about global H1 21 centimeter signal from space. And I will be covering a lot of ground across various experiments that are proposed and planned. And I want to start by acknowledging that I've taken a lot of images and content from different experiments from their official websites. So I've done my best to collect all the references for these and put them towards the end on the last slide. So for those who are interested, I can share the references with the organizers if you'd like to see them. So I have not been able to acknowledge the every single slide on each of the every image on each of the slides just for continuity. So with that small disclaimer, I'll get started. But I wanted to, instead of jumping right into the space-based experiments and prospects for this experiment, I wanted to do a quick review of what is it that we are trying to detect and why we want to look at this signal from space. So as a quick recap, this is the forest of the global 21 centimeter signals that we are all trying to detect. This covers the frequency range of about 40 to 200 megahertz with a forest of predicted signals from standard cosmological models. The solid black line is the vanilla model or the fiducial models, as we'd like to call it. I have not shown the signal from the dark ages, which is also very much a part of all the various experiments that we will cover. And that lies at higher redshifts or lower frequencies on this graph. So about 30 megahertz or below. Okay. And the thing I want to point out is that no matter where we do this experiment, that we are trying to detect this signal and we are trying to decipher and infer the astrophysical and cosmological parameters of dark ages, cosmic dawn, and reionization from this detection, there are two main categories of challenges that the experiment will face. The first are astrophysical challenges, which are inevitable. So anywhere in the universe you conduct this experiment in the local redshift, you will always have to contend with extremely bright foregrounds over the same frequency range. So the signal we're trying to detect is in red, and based on which model, the signal can be anywhere between tens of millikelvin to hundreds of millikelvin in absorption or sometimes in emission based on the model. And the foregrounds that you're trying to detect the signal against can be anywhere between hundreds to thousands of Kelvin. And this is dominated by galactic synchrotron emission. So I will not be covering it in this talk, but this is something that the field and people in the field are extremely aware about. And there are several various techniques and algorithms and methods that people have been devising and using for this separation of foregrounds from the signal. So this is an inevitable challenge that the universe presents us for the signal detection. And despite this, there have been several ground-based experiments ongoing as well as upcoming at various stages that have been taking on this challenge of detection from the ground. So to motivate going to space, first we look at what the ground-based experiments have been doing and to give credit to the tough work that they've already done. And here are some of these experiments. I have not been able to cover all the experiments on these slides, but these are just a handful of the many experiments going on the ground. So some of these are edges, LEDA, reach. And from India, from the CMB Distortion Lab at the Raman Research Institute, where I'm a member, we have had the Saras series of experiments shown at the bottom panel. And Saras has evolved across multiple generations, as you can see in those pictures. So what have the ground-based experiments already done? All right. So ground-based experiments have been critical and vital to already constraining various models and parameters of cosmic dawn and reionization. For example, the EDGES experiment ruled out what we like to call instantaneous reionization and set a lower limit for the duration of reionization to be at least 0.06 in redshift. Similarly, Saras 2 has ruled out about 10% of the standard models in cosmology. And all of these have something in common, which is inefficient heating from X-ray sources combined with rapid reionization. EDGES had claimed a plausible signal detection from cosmic dawn, which was extremely anomalous, and I'll come to that. This was in 2018. And in 2022, Saras 3 has ruled out the cosmological origins of this signal with 95% confidence and has also ruled out similar class of exotic models that give rise to deep and wide absorption troughs from the cosmic dawn. In addition to making contributions to these, to constraining the parameter space of the astrophysics and cosmology of cosmic dawn reionization, ground-based experiments have also led to significant results in terms of measurements of the sky spectrum, measuring the spectral index of the radio sky at low frequencies, deriving corrections to old all-sky maps, as well as they have been important in terms of paving the way for how to build an experiment to detect this signal. So it is important to acknowledge the ground that has been broken by these ground-based experiments. So I mentioned the signal from the EDGES detection, and you can see how different that signal looks in the solid black line compared to all the other standard model signals in the colored lines. And the Saras 3 result of 2022 has ruled out the cosmological nature of this signal. But this begets the question, what if it is not of cosmological origin, what could potentially give rise to a inference of such a deep and wide trough, which has kind of opened up a whole new can of worms. So if this signal was indeed of cosmological origin, it raises questions about candidate exotic physical models like radiatively interacting dark matter or an excess in the radio background. But if it is not real, we could potentially observe such a signal either due to poor separation of foregrounds, and also very importantly, we could potentially see such a confusing signal from instrument-related artifacts and systematics, which is what I have kind of laid out here. So the first challenge for such a detection is, of course, astrophysical, like I mentioned. The second challenge comes from experiment design itself. And I divide this into two categories. In pink are the challenges, instrument-related challenges that come from inherent experiment design. It doesn't matter where you conduct this experiment, whether you do it in space or on the ground. You have to be mindful of how you analyze the data, how you connect your electronics to one another, how the antenna beam behaves. And all of these are part of the experiment design. In addition to experiment design, another critical aspect that determines instrument behavior is the environment in which you conduct the experiment. For example, on ground, on Earth, over the frequency range of cosmic dawn experiments, which is 50 to 110 or 100 megahertz, you have a significant fraction of this band contaminated by FM radio interference. Okay, so terrestrial radio frequency interference, which goes from about 88 to 108 megahertz. That is the first challenge. The second challenge is that, remember, the signal you're trying to detect is extremely faint. You're trying to conduct an experiment that is precise and accurate to a 1 part in a million. So 1 part in 10 raised to 6. To 1 part in 10 raised to 6, we don't quite understand or know the contribution of the ionosphere. So we are looking at the universe through a screen of the ionosphere, which can itself emit, reflect, and refract. And if it does this to 1 part in a million and introduces chromaticity in the signal you're looking for, you will always be left wondering if the signal you're seeing is truly cosmological in nature or has some artifact seeded by confusion from the ionospheric effects. Thirdly, along similar lines, another issue is that when you place an antenna on the soil or on earth or in a medium, more importantly, you are bound to see properties of that medium leaking into the behavior of the antenna. So this could introduce losses in the antenna. It could introduce chromaticity in the antenna. You could find things bouncing off between the far field, such as a mountain or a tree, and being picked up by the antenna. And all of this can once again lead to confusing artifacts. So this is not a superset, but a subset of the various experimental challenges. And the ones highlighted in blue are unique to ground-based experiments. Okay, so all of these can be minimized or mitigated to a large extent by going to space. And that is precisely what several experiments are trying to do. You'll find that most of the experiments that I'll be presenting today focus on going to the lunar far side. And there is good reason for this. For example, previous experiments, even though at lower frequencies, have shown that when you're orbiting the moon, the far side of the moon completely cuts off terrestrial radio frequency interference. And recent simulations have shown that even over the frequency range of cosmic dawn and reionization experiments, the moon behaves as an excellent attenuator of terrestrial RFI. So in principle, if you're operating on the far side of the moon, you're operating in a clean radio environment. All right. And this is very important and critical for the success and to have high confidence in the signal detection that we are seeking. So here is again a subset of the various space-based experiments that have been proposed from across the world. Even though my focus will be on global 21 centimeter signals, I'm also presenting some slides on other moon-based concepts and experiments at various stages of maturity, because any lesson we learn from deploying radio telescopes on the moon, either on the far side or the near side, will all contribute towards building a better global 21 centimeter experiment on the moon. Okay, so I'll quickly cover each of these in some individual slides and we'll go on. But a special mention also goes to two experiments that I believe are selected payloads from the US, with the payloads coming from various institutes and universities across the US. One is Lucy Night, which is said to operate over 10 kilohertz to 19.2 megahertz. It will be a lander on the Schrödinger crater likely, and it will be this is close to the south pole of the moon on the far side. And among other things, Lucy Night will try to make a measurement of the global signal from the dark ages. ROLSIS, although it's not a global experiment for 21 centimeter cosmology, is also going to be an important payload. It will land on the near side of the moon and will make a measurement of the radio sky spectrum over 10 kilohertz to 30 megahertz. And all these low frequency experiments are important because remember that from ground, you are not able to make these extremely low frequency radio measurements because of the ionospheric cutoff. So this is definitely going to help further the field in terms of the astrophysics, in terms of foreground separation, as well as in terms of being able to better understand how to build and design experiments that operate either as landers or orbiters on the moon. I cannot miss this slide on an experiment that has already flown. And this is the Netherlands China Low Frequency Explorer, or NCLE, and which is part of an orbiter on the Chang'e 4 mission of China. So it was launched in 2018, and it operates on the far side of the moon at the Earth-Moon L2 point. And in November 2019, all the 3 antennas of NCLE were deployed. The statistics of the experiment are on the right in that inset picture. And commissioning phase was completed in 2020. And the science results of these experiments are eagerly awaited by the community in terms of a publication. However, we have to keep in mind that this experiment is not to be seen as a scientific detection experiment, although any such results will be extremely encouraging, but more as a precursor or prototype to better design experiments that will orbit the moon and make these measurements. So I'll first cover a couple of experiments that are more like mega experiments on the lunar far side. And these are extremely grand scheme things which involve deploying hundreds of antennas as an interferometer on the lunar far side. And we have to keep in mind that a lot of the EOR community is moving towards detection of the global 21 centimeter signal also with interferometers. So interferometers are not only for power spectrum measurements, but also can give us a good way forward with global signal detection. So FarSight comes from the US, and it will be a low frequency interferometric array on the lunar far side covering an area of 10 kilometers. It will image the entire sky over 100 kilohertz to 40 megahertz. And among its several scientific goals, one of them is to measure the dark ages signal, global signal on the lunar far side. And you can imagine that this is going to be an extremely complex experiment where you have a rover that moves out from a central station, laying dipoles across the lunar far side as it goes along 4 arms or 4 petals. And the time scale that it is expected is 2025 to 2035. Again, this is a proposed experiment in the US at different stages of review with NASA, and it's not yet been selected, but it is one of the mega experiments in the context of space-based global 21 centimeter signal experiments. Another similar concept of an interferometric array operating on the lunar far side comes from ESA. So various organizations in Europe working towards this. And this is called the Astronomical Lunar Observatory. And this is a future, more long-term concept, again, which has a lander that deploys on the lunar far side several patches of antennas in an aperture array. And this is also kind of at a somewhat preliminary stage of review, but it is expected that this might happen in various phases. So you could have one lander followed by a future mission with one patch or one arm of the array and another mission to lay out the rest. So this is again a concept that is in the works. Coming closer to home and coming back more towards global signal detection experiments, in 2018, ISRO had called for an announcement of opportunity for astronomical payloads, and several experiments along various scientific goals in astronomy were proposed. 2 of these were radio experiments. One of these is SEAMS, led by Pune University, as well as members from IIT Indore, ISRO, SAC, PRL, and IUCA. And SEAMS is an experiment that has an operating frequency of 300 kilohertz to 30 megahertz. Again, originally proposed as a lunar orbiter, SEAMS is planning now to move to a 2-phase experiment, where phase 1 will operate in low Earth orbit and operating on a PS4 rocket stage. And among various things, it will aim to measure RFI in low Earth orbit, measure the extragalactic spectrum, CMEs, and when on the lunar far side, it will aim to detect the signal from dark ages, the global signal from the dark ages. And again, SEAMS is currently in review with ISRO, but this is a noteworthy experiment proposed from India. So going to a different country now, So discovering the sky at longest wavelengths, or DSL mission, also called Hongmeng, comes from China. So this mission has about 9 daughter satellites and 1 mother satellites operating in orbit around the moon. 8 of these daughter satellites will perform as a radio interferometer at different random spacings. And one of the 9, will operate as a standalone global 21 centimeter signal measurement experiment. And it will operate over 30 to 120 megahertz. It will orbit the moon, and when on the near side, it will downlink data to Earth. And Hongmeng has employed a short monocone antenna philosophy to make the antenna as achromatic as possible, as shown in that picture down below. The top screenshot comes from the overall mission concept, where that is to be visualized as the mother antenna plus the various daughter antennas waiting to get deployed from the satellite. Hongmeng was proposed in 2015 and has been under a study phase for the past few years. And once approved, it will be ready for launch within 3.5 years, and will have a designed mission lifespan of 3 years. One cannot miss DAPPER, or the Dark Ages Polarimeter Pathfinder experiment, that again comes from the US. And it will be a lunar orbiter in 3 bands, although I believe some lander mode of operation is also being discussed. The design is very mature, and it has evolved from a precursor proposal called DARE. So DARE can be seen as this one experiment that was visualized and conceptualized very, very early on. And even though it was not selected to fly by NASA, DARE can be seen as kind of a motivation design concept from which several of the other experiments that are currently proposed have taken off. So I'd like to give a special mention to the DARE experiment. So DAPPER will operate with 3 antenna bands targeting the signal from dark ages and cosmic dawn. It will be operating in orbit around the moon, and when it is on the near side, it will downlink data to Earth. And again, this is a screenshot taken from the DAPPER mission concept. So finally, last but not the least, I'd like to come to Pratyush. Pratyush is an experiment proposed by the CMB Distortion Lab at the Raman Research Institute. Again, the same call of announcement of opportunity to ISRO in 2018. Pratyush stands for Probing Reionization of the Universe Using Signal from Hydrogen. Many of you might be familiar with the term, which is common in several Indian languages, called Pratyush. Pratyush means dawn or the sun, which I believe is an apt and fitting name for this experiment, because it will target the 40 to 200 megahertz band signal from cosmic dawn and reionization. Currently, we are working on the baseline design of Pratyush, which is refined to operate over 55 to 110 megahertz, specifically targeting the signal from cosmic dawn. And this choice was very intentional because this is the band that is most poorly constrained in terms of its science results, as well as the band that is most severely affected by terrestrial RFI due to FM. So the lunar orbiter will be custom designed for the primary science goal of detecting the signal from cosmic dawn and reionization. A lot of the design philosophy comes from the ground-based experiment Saras, but there are specific design choices where we have had to deviate from the Saras experience to customize this payload to do justice to operating in space. I'm happy to report that after just completing 2 years in seed funding stage, Pratyush has been recommended to move to project mode by a technical review committee appointed by ISRO. And now we are awaiting review from the Apex committee of ISRO to get the go-ahead and move on to the next phase and eventually to engineering and flight models, pending project approval. So here is the concept of Pratyush, where you can see that Pratyush will be operating on the lunar far side. When it is in the shadow of both the Earth and the Sun, it will collect scientific data. When it is on the near side, it will transmit data back to the Earth. And when it is in view of the Sun, it will charge batteries using solar panels. So this is the baseline concept CAD model. The gray structure is a uniquely designed, custom designed cone antenna over a profiled ground. And this has very specific properties to ensure relatively achromatic antenna beam as well as smooth coupling of the signal from the antenna into the electronics beneath it. All the electronics is contained in the bus structure, so that shares both the payload as well as the spacecraft electronics. And important to note here that at various stages, we have to take care of the EMI shielding, which is essential because you don't want to go all the way to lunar far side to avoid radio frequency interference, but then be contaminated by self-generated radio frequency interference. So we have to take extreme care in making sure that we are not dominated by self-generated RFI. So you have solar panels that get body mounted on the sides of this bus structure. And like I mentioned, when you are in view of the sun, that will help charge the batteries that will run the experiment. The proposed mission lifespan for Pratyush is about 2 years. So this is the current stage of Pratyush developments. You have 3 main subsystems, namely the antenna, which is as evident will collect the signal from the radio sky and pass it on to the receiver. The first element of the receiver is the analog part, which conditions the signal as well as calibrates the signal. And finally, you have the digital receiver, which is based on an ADC and FPGA based electronic structure. And all of this gets connected to a satellite or a bus. So like I mentioned, the antenna is custom designed and we pay specific attention to the beam of the antenna, how it behaves as a function of frequency, as well as how it couples the signal from the sky to the electronics beneath it. And a special thing to mention here is that given that the body of the antenna sits right over a block of metal, which is a satellite bus, the satellite bus is also very much a part of the electromagnetic structure of the antenna. So any change or modification in the bus structure that could very well come from iterations with ISRO will end up leading to some design changes in the antenna itself. So after several iterations, assuming a CubeSat-like bus structure, we have arrived at this version of the baseline antenna design that we are satisfied with. And we verify this by running the signal through the antenna all the way till the end using a signal detection pipeline that we have come up with. So the Pratyush analog receiver, like I mentioned, has various electronics to calibrate the signal to make sure that the power levels are okay. And in addition, a conscious design choice that we have made with Pratyush, which is not there in the current ground-based counterpart Saras-3, is that we have a way to measure the antenna return loss or the way the antenna couples to the electronics beneath it in situ. Because the conditions behind the moon can keep changing the antenna properties, because remember that this entire payload goes in and out of the shadow region behind the moon, and you expect a lot of thermal fluctuation or thermal swings. And this can cause changes to the antenna's mechanical and hence electromagnetic properties. So we have an inbuilt or in situ VNA or vector network analyzer, like we call it. And this is custom designed to operate as part of the antenna, as part of the RF system. And finally, coming to the digital receiver, like I mentioned, it's an ADC and FPGA based receiver. And the one important design change that has happened from ground-based experiments is that we have moved away from a laptop to a small Raspberry Pi 4 card for the ground-based lab model. So basically, the idea is that you are doing away with the requirement of a large laptop-like electronics to control and monitor all the operations to a small single board electronics, that single board computer that does this monitoring and control operation. So the entire lab model is based on ground-based electronics. So none of this are space qualified yet. We will get to that phase shortly, hopefully pending our Apex committee review from ISRO. So just for a sense of scale, this is what the entire payload and experiment is envisioned to be. And given that we want to operate in an extremely pristine environment without any other coupling to near field objects or RFI, we envision Pratush to be a dedicated experiment or a craft without any other payloads and without any other experiments piggybacking along with this bus. So we have been looking at various simulations for orbits of Pratush around the moon, and we have some basic estimate of what we are kind of looking for. We will prioritize two things, namely the stability of the orbit so that we don't require frequent orbital correction over the mission lifetime of 2 years. And we also want to maximize the time spent in the far side of the moon in the shadow of the sun and the earth. So we call this the prime cone region. And we believe we need a few 100 hours of this. And we have some basic orbits in place that we have proposed. But again, we will work closely with ISRO to finalize this. However, we have an intermediate phase. So we want to propose Pratush in two phases, namely phase 1 in low Earth orbit and then phase 2 in lunar orbit. So the low Earth orbit already gives us a lot of advantages compared to ground-based experiments and also compared to the moon. So first of all, the cost and complexity is lower. The windows of opportunity for launch are more frequent. We are able to make measurements of the sky spectrum, as well as we are already resolving two of the three main issues that plague ground-based experiments. So although we will see terrestrial RFI from FM, we will still be above the ionosphere. We will still be away from near field effects. We are operating in free space, so we don't have issues of the antenna and the experiment getting coupled with the ground beneath or with the soil beneath it. So we expect that a combination of Pratush in low Earth orbit, along with complementary measurements from Saras operating on the ground, will give us an extremely clean and high confidence detection and will potentially motivate going to the lunar far side if required. So we have a kind of low cost yet high returns type of opportunity as a low Earth orbiter. Here, I'd like to mention that we've already started a set of simulations to get an understanding of what kind of FM-based radio frequency interference we will see in low Earth orbit, so that we can also factor that in and try to optimize orbits such that we minimize the amount of terrestrial RFI that we are bound to see. This paper with an algorithm called Starfire has already been submitted, which gives an expectation of FM-based RFI in Earth orbits. So this is what we expect. On the left are already the models in the maroon color that have been ruled out by Saras. So Saras 2 has ruled out some of those standard models, and Saras 3 has ruled out those exotic models. On the right side, we have those forecasts for Pratush. The blue set of lines are what Pratush in low Earth orbit will be able to constrain. And a combination of the red and blue lines are what the lunar orbit Pratush, so phase 2 Pratush, will be able to constrain. So with that, I'd like to wrap up in a couple of slides. So I don't want to paint a picture that space-based experiments are a piece of cake and they're going to solve all the problem of ground-based experiments, because they come with the challenge of added cost, complexity, and the inability to go and fix things on the field. For example, experiments that land on the lunar far side have challenges of deployment, operating on a terrain or a ground that is unfamiliar territory, and you don't know what effects the lunar regoliths will have. The orbiters will have to deal with self-generated RFI because your antenna is sitting right on top of electronics, as well as you will have thermal swings. You have to contend with challenges of data downlinking because you don't have gigabits Ethernet links running between the moon and Earth. And each experiment employs its own technique and philosophy to kind of mitigate or address each of these challenges. However, the way forward is that you do need multiple experiments on the ground as well as in space to finally nail the astrophysical problem that we are trying to look at. As much as you can think of it as a friendly competition, a confirmation from multiple experiments, both from the ground and space, is the way forward. including interferometers as well as single antenna experiments, because all of them at the end will help address the actual astrophysical parameters that we are trying to detect. So we have a lot of exciting times ahead, and it's a matter of time. The community is eagerly waiting to watch which of these experiments get picked to fly, how they fly, what their results look like, and certainly exciting times ahead. And with that, I'll leave this up on the screen. A bunch of references from where I've drawn a lot of this information as well as these images. And like I mentioned, I'll be happy to share this with the organizers to distribute to those who are interested. So I'll stop there to take questions. Thank you. Thanks, Prabhu. Yeah.
If there are any questions for Mayuri, and, we will just pass the mic around.
Yeah.
Regarding Turkish, what is the mission that you think
Right, Prabhu. So, the good question. Right now, the stage is that we are awaiting a review from the committee that is in a position to give us the go ahead. Hopefully, once we get the go ahead, we hope that we'll be able to have a space worthy experiment ready to fly in about 2 years. And since we expect to be a dedicated craft, like a dedicated experiment, what we look for is an opportunity to go in one of these ISRO small space launch vehicles or SSLVs and just get jettisoned or deployed in low Earth orbit. So we're not necessarily waiting for some other bigger experiment to combine with or to piggyback on. So timeline will be determined by mostly whatever earliest launch they can accommodate us on. So tentatively, after approval, we are thinking about 3 years. We will be generating our commissioning results from low Earth orbit. Lunar orbit timeline is unclear at the moment, but we're hoping that low Earth orbit may be about 3 years. Right. So I think right now it's happening more. Sure. Sure. Yeah. Sure.
Sorry, the first question was about when the mission is likely to happen, and the second one that I was just asking is, since the space-based missions are very expensive, space-based missions are very expensive, and how and complex, and also time involved, and so on and so forth. So how the global community who are launching or coordinating these operations? Are there any coordinated operations so that people can complement and not repeat things which are possible and so on? So that was the question. Thanks, Mayuri. Please address this question.
Yeah. So right now things are happening a little bit more informally. So the community has been good about talking to each other in various meetings and conferences and being open to receiving and providing critical feedback. Several of us are actually reviewers for different other competing experiments, including myself. So that gives us a good, so it's kind of happening informally. And of course, within various countries and space agencies, things are, it's not a single institutional effort across US and, for example, Europe. We've already seen Netherlands and China work together on the NCLE. So there are things happening, but the various conferences and meetings, like, for example, these are the ones that are a good platform where discussions are ongoing. Nothing formal yet, though. Yeah, thanks, everyone.